So we started talking about the boosting paradigm, and as I said, this is a very practical approach to learning. Because the boosting paradigm is trying to overcome the computational complexity that we have seen to many very natural learning tasks. So as a step, the first step, so we say as an algorithm, so just recall what we've done so far last time, that we say that an algorithm A is a gamma weak learner for a class H if we have a function if for some function m of 1 over delta for every probability distribution d over x and every function f in H the probability over samples taking from df to the m. So this just means, this notation means that the sample are IID drawn m many times, and each time I draw a sample, I pick randomly from D and label it according to F. Yeah, it could be m. It doesn't matter, m of delta, m of 1 over delta. It's the same thing, right? Okay, I don't mind. Let's make it m of delta, right? But it will be an increasing function of 1 over delta, right? Okay. So what I'm saying is that we look at samples drawn IID m times from D and labeled by F. We feed this sample to our algorithm, and we check its error. So we look at LDF of A of S, and the probability that this will be greater than half minus gamma is less than delta. What have I done wrong now? Okay. Okay, so this was our definition of weak learning. So let's just go over the definition, make sure that we all understand what it is saying. So we have a fixed learning algorithm. I mean, it will be learnable if there will be such an algorithm. And we have sample complexity that depends only on the parameter delta. And now we are back to the realizable case. So we got used for the past, most of the time we're talking about the agnostic case. Now we are back to the realizable case. So in the realizable case, rather than talking about an abstract any probability distribution P over X and the labels, here I only have a probability distribution over the domain X, and the labels are generated by some function from the class, because it is realizable. Right? So we have this sample size bound. And if we saw a sample of sufficient size, so we need here for every m greater than m of delta, if the sample size is big enough, then we look at our error with respect to drawing a random point x from D and labeling it by F, and we compare it to what A of S is saying. The probability of error should not exceed half minus gamma. So the only difference between this and the usual definition is in the usual definition we had here m of epsilon and delta, so it's epsilon delta instead of just delta. And here, instead of this fixed arrow, we wanted to achieve arrow epsilon. So we just fixed the gamma here. Right? And we will actually, in all our cases of weak learners, we will restrict our attention to a very specific type of weak learners. So we will focus on weak learners of the type ERM B for some basic class B. So what we're doing now is we say, instead of talking generally about weak learners, we will focus on weak learners that are just ERM. So what have I changed? Now, why not ERM over H? Because we will consider classes H that ERM over H is difficult to compute. Instead, we will compute ERM over some very basic class B that will be easy to compute. So we will have here an interplay between two types of functions. The complex functions of H that we are trying to approximate, to learn, and the simple functions from B that we are using as a subroutine in our boosting algorithm. But we haven't seen the boosting algorithm yet, so what have we seen so far? We've only seen one thing. So what we have seen is only one example. We have seen one example. And here we had H was the class H3 over R, which was the class of all functions which are just a partitioning of the real line into three segments. So these are all the functions that are just a partitionings. I have here R1, R2, partitioning the real line into three segments. And I give them alternating or arbitrary labels for every segment. So this is my class H. And as the basic functions, I took H thresholds, which is just one cut in the line. And we saw that for every, so we saw the claim that we have proved. One claim was that for every sample S labeled by a function f in H3, there exists some H in our simple class B, the threshold functions, such that the loss with respect to the sample of H is at most 1 over 3. This is what we saw last time. It was very simple. A corollary from this, is that ERM over B is a weak. Now I have to pick gamma. So I want to say it's a, let me write it like this. It's a weak gamma or gamma weak learner. A gamma weak learner for my H3 for, well, gamma equals what? What is going to be gamma? Yes. Okay, almost. Almost. So someone already commented. Why not? So 1/6 looks like the right number here, right? Because I get here an error of 3, which is a half minus 1/6. But there is a small caveat here. What is missing? What is missing is that here we wanted to make sure that the true error is at most half minus gamma. And what we get here is that the empirical error, this is at most half minus 1/6. There is still this potential gap between, I can guarantee that the empirical error is not too big, but the definition requires to control the true error. So what can I say about the true error? And for the true error, I just say, OK, but the point is that we know that this class B has VC dimension 1. So for every, no matter what the distribution is, for every distribution, if I have large enough samples, I can, the empirical error approximate the true error. So where gamma, all we need is where gamma is less than 1/6. Because, or if you want, 1/6 minus something, right? Because given gamma less than 1/6, let epsilon be such that gamma plus epsilon is less than 1/6, and pick let m of delta, the question is, what sample size do I need? B m b of this epsilon delta. I hope that I'm not getting you completely confused, because I'm just playing with notions that we have seen. What does this guarantee? This guarantee MB, this number, if I have such a sample size, it guarantees, it will guarantee that the true error with respect to any distribution, so in particular the f, of the output of my algorithm, say h, which is ERMB of my sample, it will guarantee that this will be at most the sample error of ERMB over the sample plus epsilon, which will be at most 1/6. Right? Because I wanted that we know that gamma plus epsilon is at most 1/6. I picked gamma small enough such that when I add this epsilon, I will not go over 1/6. So for all of you that got confused, I mean, it's kind of thing that I'm sure that if you go over it on your own, it'll be clearer than just listening to me. The only small caveat that we had here is the issue that we controlled the sample error. We needed to control the true error. But by picking large enough sample, I can control the true error. So the conclusion is that ERM with these signed threshold functions is a weak learner for any gamma smaller than 1/6. It's a weak learner for the class H3. Yes?
I just want to say 1/3 is not equal to 1/2 minus
What?
1/6. I just want to say 1/3 minus, does not equal to 1/2 minus 1/6.
No? I think it is. 1/3 is 2 sixes. That's 3 sixes. And that's
elementary math.
yeah, right. Yeah, okay. So this is the conclusion from last time, and now we want to, so far we just cleaned out and reviewed what I did last time. And now we talked about weak learners, we talked about weak learners of this type, but we haven't seen yet how weak learners can help us to get strong learners, which is the whole point of boosting. So let me, even before I go in, the weak learners algorithm that is really useful in practice is very simple to this kind of weak learner. So in practice, the most popular weak learner is the class of HDSD, which means the class of decision stamps over RD. So what do I mean by the class of decision stamps over RD? The decision stamps, so what we are, the kind of classifiers that we allow in our basic class, the most popular weak learner class, our B. The classifiers that we allow is I take a sample here, and I allow myself to either project it on this axis and label all of these as minus, say, or plus, and all of this is minus. So either I project it on some dimension and take a threshold in this dimension. Or I can project it on this dimension and take a threshold function on this dimension. So if you have data in RD, our basic class is going to be the class that chooses a dimension, projects the data on this dimension, and uses threshold on this dimension. So this is the class of decision stamps in dimension D. If I want to write this class explicitly, what it is, so every H in this class, H decision stamps over dimension D, is determined by two parameters. One parameter is I, and the other parameter is R, or actually 3 parameters, because I also need a sign. And here I need a sign, either plus or minus 1. And H, I, R, say plus 1 of a point X in RD. What does it do? It is minus 1 if the ith coordinate of x is below r, and it's plus 1 if the ith coordinate of x is above r. Right? Where x is x1 up to xd. What am I? Again, I have a classifier which is determined by 3 parameters, I, r, and either plus 1 or minus 1. This classifier, when applied to a point x is a vector. This classifier, when applied to a point x, should give us a label, either minus 1 or plus 1. How will it determine the label? It will take the point x and only consider its ith coordinate. It does a projection on the ith coordinate. This is the role of I. I project it on the ith coordinate. I only consider the ith component. Now I look at the ith component and ask myself, is it below or above r? And I label accordingly. And the minus here will just be the flip of these two labels. So this is exactly what we saw here. You see, if this were my coordinates, this was h1, say this point is 7. So this was h1, 7, minus 1. Because I projected on the first coordinate, my threshold was 7. Below the threshold, I gave it plus. Above the threshold, I gave it minus. So it was the minus 1 guy. This guy here, again, these are my 2 coordinates. Say the height here was, I don't know what, 2.6. So what was this classifier? This classifier was h2, because I projected on the second coordinate. My threshold was 2.6. And my label was plus, because above it I signed it as plus, and below it I signed it as minus. So every classifier in this class chooses a coordinate, projects on the coordinate, and takes a threshold in this coordinate. This will be a very useful basic class. We have already, this is exactly the B that we have discussed here, but here the dimension was only 1. And we extend it to arbitrary dimension. Am I confusing you in any way, or what? You're too quiet. I mean, what? Are there questions about the definition of the class? Is it clear? Okay, so now I want to show you, I should show you 2 things. One of them is that, why should I use this class? I want to show you that this class is efficiently learnable. ERM over this class can be implemented efficiently. Then we will show how, if we have an efficient learner for the basic class, we can boost it to a learner of a bigger class. So the next claim that I want to show, so we define this class. Let me leave this definition on the board. So now I have a simple claim. Claim for every D, the class that I'm going to use often as my basic class, H decision stamps in dimension D, is efficiently learnable More concretely, I can tell you what the algorithm is. ERM over this class, ERM over this class HDSD can be implemented in time O of MD. Remember, when we talk about the running time of an algorithm, it's a function of the input size. So this is the input size. Of course, I will have to tell you what is the connection between M and the required precision parameters. But if I have a sample of size M, I can implement it efficiently in the sample size. What is?
It's slightly confusing to have D in
Oh.
dimensions and this sample size.
What? No. D is the number of dimensions. It's the same D.
Oh, it's just the number of dimensions.
D is the number of dimensions. So this is M times D. D is the number of dimensions.
Okay.
And M is the sample size. Okay. So how will we implement it? So the proof is very easy. How do I implement ERM in dimension D? ERM over this class in dimension D. So you get a sample. So your input, you have an input, which is a sample S, X1, Y1, up to XM, YM, where each xi is a vector in Rd, and the yi's belong to +1, -1. And now we want to output the best decision sum, the one that minimizes the error over this sample. So anybody has an idea how shall we do it efficiently? What I'm saying is this class can be very efficiently implemented. Yes?
For each dimension, you can consider line only that are on the points, right? So you can scan it the first time, count the number of ones that are above and below, scan again, find the maximum, return it for every dimension, return the maximum.
Right. So basically, the advantage of this class is that every dimension here is independent. I have to pick the best dimension. So for I going from 1 to D, I want to handle the dimension I, project the data on this dimension, and consider the best HI, the best threshold function on this dimension. So when I project the data on a dimension, what I get is I have my sample points. They're all projected on one dimension. They all look like this, and they are labeled +1, -1, -1, +1, and so on. Now, once I projected it on a dimension, how many candidate threshold function do I have to consider? Potentially, how many threshold functions are there in general? In general, there are infinitely many threshold functions. But given the sample, if I just want to talk about the best one over the sample, how many threshold functions do I need to consider? Yes? M, or M+1, right. Just M+1, because I have here M points, which are the projections of those M points. And I just have to consider what will happen if I take a threshold here, what will happen if I take a threshold here, and so on. So for each, and now we picked an I for each I. Now for each j between 1 and M, consider the function h which is determined by projecting on this coordinate I. Now as a threshold, I will take, say, the point x, j, or xj, its i's coordinate. And I will consider plus 1 and the same thing, h, I, xj, its i's coordinate, minus 1. So I will just consider cutting at these points. So I have to consider m or m plus 1 hypothesis for every dimension and go over all the dimensions. So it will take me time, which is basically m squared times d. Because for every such hypothesis, all I have to compute and compute the sample error of this h for each such h and output the minimizer of this error loss. Yes?
You wrote O at D, but it's not M squared D.
Right. Good. You are, I think, a step ahead of the rest of the class, but I will get to it in a second. What? Just for being smart? No. I mean, being smart already gives you an advantage, you know. So what I'm saying, the implementation is very simple. I have D projections to consider. In every projection, I have to consider just cutting at the threshold determined by every point of my sample. So what is the sample complexity here? How many hypotheses do I have to check? We need to evaluate how many hypotheses. I'm doing just the sample complexity, the computational complexity analysis. Need to evaluate how many hypotheses, how many H's do I need to evaluate? I look at every possible projection, and in every projection I look at cutting at every point there. So how many hypotheses do I have to evaluate? In total? 2MD, right. 2M plus 1, there is also the times D. Once I pick a direction, once I pick the projection, I have to consider the threshold at every point, times 2 because I have the plus 1 and the minus 1. So many hypotheses H. And how much time does it take me to evaluate one hypothesis? I need to calculate its empirical error. So how many checks do I have to do to calculate its empirical error? Yes?
The first one is M, and all the ones after are 1.
Nice, very nice. Very nice. Right, so roughly speaking, I will need, and now we need in principle, we need M checks to evaluate LSH for each H. And this will result in M squared times D. But as you notice very nicely, I can say I don't have to. You see, if I have an H, I have an H here, and I have my points, and some of them are labeled plus, some of them are labeled minus, and I want to evaluate its error. In principle, I have to see every point, check every point, whether it's error or not, error or not, error or not, error or not, M checks. But if I arrange the points in order, and then I just move the H each time by one step, then at each step, I only have to check one point. By moving in this direction, did I gain or lose an arrow point. So I can make if I order the points and order my h's that I check, incrementally to go from one h to another h, I just need to check how did the labeling of this point change. Did it go from arrow to non-arrow, or did it go from non-arrow to arrow? And update the arrow of h. So in total, I can do it in just time, which is m times d. Yes?
If you order them, wouldn't you need to sort it with m log n?
I'll need another m log n for ordering it. That's a good question. How we need to order them? Yeah, that's painful. No, I don't think so.
Do they say bucket sort and then?
No, we don't need any bucket sort. I mean, they are given to you as, yeah, I just assume here that we order them in constant time,
Yeah.
but
They're on different dimensions, so you have to reorder.
and also it's just added, right? Oh, because I have to order them on every dimension, so I get to order them. Maybe she's right. To order them on every dimension, I'll need d times m log m. This is just to order them. Now I have the order of every dimension, and now I'm just running in time 2m plus 1 d. It's not multiplicative because I don't have to reorder every time I check an h. I order it once in every dimension. That's what it costs me. And then once I have this order, I'm running it in this time. Okay. What is wrong there? That I forgot the log factor? No.
No, it
Yeah.
would be big O m log n, right? Instead of, because m log n is bigger than m plus 1.
Yeah, it will be O. It will be O tilde here if I ignore log factors. Oh. You haven't seen this notation? This is very common for lazy people. You want to ignore log factors, you add a tilde here, and it's common notation for ignoring log factors.
Can we do this on exams?
On exams in machine learning, you can do it. Okay, so I think we spent more time than it deserves on this simple algorithm. So what is the conclusion? Okay, so our conclusion is that we have this class of very basic classifiers, the class of decision stamps, and we can implement their ERM efficiently. And now finally we want to see the boosting algorithm. How do we boost weak learners to get a strong learner? So the boosting algorithm, the idea of the boosting algorithm, the boosting algorithm paradigm so our input, we get as an input, we get some labeled sample, a labeled sample, S equals x1, y1, up to xm, ym. And we get as an input some weak learner that will be usually ERM of some simple class. We get some weak learner, and we get some t, which is a number of iterations. Now, how does the algorithm proceed? The algorithm looks at this sample. The idea of the algorithm is as follows. We look at the sample. Here is, say these are my sample points. And they're labeled +1, -1, and so on. I feed the sample at every iteration. I will feed the sample to the weak learner and ask the learner to give me the best hypothesis the weak learner can find. Now, if I feed the same sample over and over to the weak learner, I'll get the same answer over and over again. I'm not getting any progress. So the trick is that I first feed, each time I change the weights of the points. So for each iteration, one or two T's. For each iteration, we will, iteration T, we will fix a probability distribution dt over x1 to xm. So we can think of it as what is the significance of every point. And d1 is just going to be the uniform probability distribution. 1 over m, 1 over m, up to 1 over m. Now we have to define what is dt plus 1. So we get dt plus 1 by first applying ht, which is the weak teacher applies to the sample dt weighted by dt. So I feed the sample weighted by dt to my weak teacher. This is the distribution that the weak teacher is trying to learn. I feed this sample to ht, and increasing the weight, the d probability of each xi on which ht errs, and decreasing the probability of each xi on which ht predicts yi. So the idea is you take your sample, you feed it to the first learner h1. The first learner h1, the weak teacher h1 makes some errors. So if I look at my sample, after applying h1, I have to correct, error, correct, error. That was the result of applying h1. So now when I'm going to apply the weak teacher again, what I will tell it is to focus on the points on which the previous one made an error. So what you're asking it, you are increasing the weight of these points. The probability distribution now will increase the weights of this point. Now this is a probability distribution that I can ask my weak teacher to learn. It will take a sample from this distribution. He is more likely to see points on which the previous round didn't make an error. And we apply the weak teacher again. Now he cannot afford to have errors on all of these points because those points are very likely to occur a lot. They have high probability. So the new h should be correct on the points where the previous h made a mistake. And this way we keep iterating. So we have, each time we update the probability distribution, feed it to the weak teacher, and get a new hypothesis, ht, which is the weak teacher, applied to the updated probability and the fixed sample all the time. And the question is, so we get a sequence of h's. h1, h2, ht, up to ht. This capital T is the parameter of for how many iterations do we go. Now we have a collection of hypotheses. The question is, what is going to be the output of my algorithm? So the output of all this procedure, output is the function sine of sigma I goes, or T goes from 1 to capital T, of WT HT for some WTs that we need to determine. So that's basically the algorithm. So what does the algorithm do again? You take your sample, you define a distribution over this sample, and send the weak teacher to classify this sample. You get the outcome. You look where it erred and where not. You update the distribution. You want now to focus on the points where the previous HT made an error, and feed it again to the weak teacher. So at each iteration, the weak teacher gives you some hypothesis. At the end, you take the weighted majority of all of them. So we can think of this thing as a weighted vote. I get a point x. I see each of them whether it gives me +1 or -1. I multiply it by a weight and look at the majority. The sign will be the majority, the weighted majority of the predictions of the different HTs. Right, so to make it into a clear algorithm, I have to tell you two things. How to update the distribution dt, and what are going to be those weights at the end. OK, yes?
So I'm confused about what the teacher is. Is this ERM over whatever the class of H is? Is that so it's the weak learner over our, there's like a
OK, so what does the weak teacher do here on this distribution? So the weak teacher of this distribution, we can think of it as he picks a sample of some fixed size m according to this distribution and applies ERM over this sample. But we will see that we can reuse all the time this sample, but just give weights to every point. So every arrow will count. Every arrow will count according to the weight of the point.
And so is the class, is this B? Is the class?
The B is hidden here. The B is hidden in my definition of the weak teacher.
Right, I'm just trying to figure out where the H's are coming from.
The H's are coming from the weak teacher. If the weak teacher is ERM over B, they will all be from the class B.
Okay.
Right. That's a good question. Because I was talking here on two different things. I was talking about ERM-B, and now I'm talking about general learning with weak teachers. Most commonly, the weak teachers will be ERM-B. But the definition is more general than that. So all I need to give you is two parameters. How do I update the distribution, and how do I take the weights at the end? Yes?
When you increase the weight on the things that are wrong and decrease the weight on the things that are right, wouldn't you run into the risk that your new weight teacher is going to make more mistakes on the things that
Yeah, I do. Yeah, that's a good point. When I increase the new weak teacher, if I had here this was the outcome, the arrows and non-arrows of HT. And now I'll take HT plus 1. HT plus 1 will have more weight. He will care more about these points. He will care less about these points. So he may make an error at a point that before was correct. That's why I don't use at the end the last H. What I use at the end is the combination of all of those H's. It's not, I could say at each iteration H improves, and at the end I give you the last H. But that's not what's happening. Each iteration gives a different arrows and non-arrows, and at the end I just take a weighted vote of all of them.
Why does this work?
OK, so that's what we're going to do next. We will show what does it work, right? Yes.
What's the relationship between dt and s?
dt is a probability distribution over the set S.
Oh, so s is set, not sample.
S is a sample, but when I say dts, it's each point in the sample gets probability determined by dt. A sample is just a collection of m many points.
You said s is the same.
What?
I think you said s is the same, right?
S is the same.
So it's not generated every single time.
No, it's not generated every single time. So so we will define some, yeah, I mean, S could be generated each time or be the same set. We will take the version that it's the same set. So what do I mean by DTS? What do I mean by applying the weak teacher to DTS? So what we will do is we will define, so given dt of x1 up to dt of xm and sum h going from x to plus 1 minus 1, we will define the arrow, or let me just call it arrow, with respect to dt of, to dt in the sample S, of h as the sum over I goes from 1 to m of dt of xi times 1 h of xi not equal yi. So what does this function do? This function, I want to know with respect to this distribution, what do I mean by the arrow of h? So what do I mean is that you look just at the points in which you made arrow. If you didn't make arrow, this is 0 and you don't care. If you made an arrow, this is 1. So whenever you made an arrow, you take the arrow and multiply it by the weight of this point. So you care more about not making arrow on heavy points. And you care less about not making arrow in the weak points, in the light points. So instead of resampling each time, I can fix the sample and just use this to estimate my error. Yes?
S may contain non-unique points, right?
S may contain non-unique points.
So the distribution dt is...
Yeah, so it's OK. So if you have the same point repeating, dt should give you the same weight. Yeah. So we have the boosting algorithm up to fixing the parameters of how we update dt and how we choose the WTs at the end. But the basic idea of the algorithm is you run the weak teacher, you get errors, you update the weights to emphasize the errors, run the weak teacher again. And repeat and repeat and repeat. And at the end, you take a majority vote. And the big question is, like she asked, why does it work? And that's what we were supposed to do today. But we'll see how much time we have. OK. Are there any more questions about the idea of the algorithm? I mean, you take the weak teacher, and you throw it in the data. And then when it makes an error, tell you, now you repeat it, but you emphasize on your errors. But I allow him to ignore the points that he already made correct predictions on. And then he's emphasizing on the errors, and we repeat it. OK, so we only need to define the parameters. And the parameters really depend on which flavor of the boosting algorithm one uses. The most common boosting algorithm is called AdaBoost. The AdaBoost is the most common version of this algorithm. And for this AdaBoost, all I have to give you to define a version of this algorithm, I have to tell you just these two parameters, how to update weights and how to choose WIs at the end. So AdaBoost updates weights as follows. So for the AdaBoost algorithm, d t plus 1 of a point xi is equal d t of xi times e to the minus, and now I have to look at my notes not to make a mistake here, w t times yi ht of xi. Okay, so this looks, and this is also divided by normalize. Okay, so what is this? Note that what we have here, yi is the label, ht of xi is the prediction. If the prediction was correct, what is yi times ht of xy? When the prediction is correct, what is this? Yi is either plus, minus, or minus 1. Ht of xy is either plus, minus, or minus 1. When the prediction is correct, what is this product? Plus 1. When it's correct, it's plus 1. So I multiply it by e to the minus something, so I decrease the weight. It's the old weight multiplied by e to the minus something, I decrease the weight. When my prediction is wrong, the label of yi is different than the label here. I get here a minus 1. So I get here a minus 1. So I multiply it by e to the plus some number. So I increase the weight. E is the base of the natural log. Right? So this formula tells me whenever you are correct, decrease the weight of this point xi. And whenever you are wrong, increase the weight of this point. What I still need to tell you is what are those WTs. And those WTs are the same weights that we will use also at the end when we output our final hypothesis. Those are the same WTs. So WTs WT is going to be it's some formula half log 1 over the error over dt s of ht minus 1. Again, I mean, the formula looks confusing. Let me just explain to you what it does. So this is the weight that I'm going to give to every hypothesis. Now, this weight depends on the error. If I make a big error, you see, so the weight depends on the error. The smaller the error, how does it go? The smaller the error, do I give it more weight or less weight? If it makes a small error, do I give it more weight or less weight? If it makes a small error, I give it a big weight. If it makes a little error, I give it so small error, big weight. So small, the weight, that's the main thing, is inversely proportional to the error. So I check my error of ht. I check the error of ht as we defined it here, the error of ht. We check the error, and we give weights which are bigger weights for when you are more correct and smaller weights when you are less correct. And those weights play two roles. They tell you by how much we update each time. And they tell you how much this HT will weigh at the end. At the end, we will give more considerations to HTs that gave small errors. So that's the whole algorithm. So the whole algorithm is we go in iterations. In each iteration, we invoke the weak teacher, update the probability, make it focus on the errors before, run the weak teacher, and move on. And note that this whole implementation is very efficient, provided that the weak teacher can learn efficiently, because it's just iterations of invoking the weak teacher. So this is the AdaBoost algorithm. It's a very practical and useful algorithm. What we want to do next is to analyze it and see why it works well, or under which situations it will work well. Any questions about the algorithm? Again, I don't really care about the exact formulas here and here. All I care about the flavor of these formulas. The flavor is we give more weight to, the more correct you are, the better weight you get. And here, when you make an error, the point is now going to weigh more. So the next thing I want to do is an analysis of this algorithm. And I think the first step towards this analysis is to look at what is the outcome of this algorithm. So analyzing the boosting algorithm. And the first thing I want to know to note is that let us consider the class of outputs of boosting. So when our weak teacher, weak learner, weak teacher is me, right? Weak learner is ERMB, right? The output belongs to the class that I will denote by L. I just want to make sure that I'm in line with the book notation. Yeah, L of BT. It's the class of all functions of the type sine of sigma I goes from 1 to t of Wi hi, such that the Wi's are real numbers and the hi's belong to B. So the output belongs to this class. The output is always a weighted sum of members of B. And the weighted sum has at most t components. Let's call it t goes from 1, and let's make it wt ht to be consistent with the notation before. So we have two components. I thought you were correcting something on my formula.
No, I'm not that.
Okay. So the output is always such a weighted sum. So we moved from a class B, which was a very simple class, to a more complex class, which is all the signs of weighted combinations of this B. And what we will want to analyze is the complexity of this class. So now we'll need to analyze two things. What is our, remember that usually the true arrow of some h is bounded by the empirical arrow of h plus some function here that has to do with the VC dimension of the class. Some function we usually had here square root and VC dimension of my class plus something delta plus something depending on m, right? That was our usual bound. The class here that we are going to worry about is this class L of Bt, because that's what we are giving an output from. And so we'll have to worry about two things. What is the error of my combined h over the sample, and what is the VC dimension of this class, because this tells me how far is the empirical error from the true error. Yes?
So we're turning into non-uniform learning?
We are turning into not non-uniform learning. No, it's not non-uniform learning.
But this formula comes from non-uniform learning.
No. This formula doesn't come from. This formula is our basic fundamental result of machine learning. That your error, if you learn h from some class h, then here m over h makes an error at most this. Or that's the basic fundamental theorem of the machine learning.
Because the idea you punish a function for its complexity.
Right. But here the complexity comes into choosing the class. I choose the class T in advance. I choose the number of iterations in advance, and I analyze it with respect to a fixed T. If I would let T grow and not fix it in advance, you are right. It will be non-uniform learning. But here in the analysis, I fix T. If I fix T, it's a fixed class. That's the VC dimension of this class. But we will need to analyze these two components. So the first thing I want to do is just show you that this class is very rich. So demonstration of the richness of this class L of Bt. So let B be the simplest class, the thresholds over one dimension. Decision stems on over one dimension. What will we get with HT? So I claim that the class L of Bt contains all functions over R that have at most T segments. So I mean the class, so let us define. If I take here R1 to RT, and I look at the function which is plus, minus, plus, minus, plus, minus, plus, the function that has alternating signs according to any choice of R1 to RT, I'm claiming that every such function can be described by a weighted combinations of at most T components that each of them is just a threshold function. So I'm saying I want to show you that by doing those weighted combinations, we are getting a much richer class. So we start with the class of just threshold functions. And I claim that if we take T combinations, we can get any partitioning of the line into T plus 1, minus 1 segments. And how are we going to get it? So if I have here thresholds R1 to RT, you just have to note that this function, so let's give this function a name. So this function, let's call it f. So I claim that for every x, f of x, so f of x is just this sign, is the same as the sign of the following combination. And what is the following combination? Sigma wt ht, where wt w1 is 0.5, and for t greater than 1, wt is -1 to the power t, and ht is just the threshold at the point rt. So what I'm claiming is, in order to get this function, I will take the ht's, which are these thresholds, and I'll give them the following labels, the following weights. The first one will weight half, and then I'll have alternating +1, -1 weights. And why will it work? I'm claiming that for every x, this sign will be the same as the sign that we assign here. Why will it work? Because if I pick a point here, so if I pick a point here, all the t's are going to give it okay, let's make a picture. So what we have here is the first function gives me this. The first h1 gives me this labeling, +1, -1. Right? h2 gives me some other labeling. h2 gives me the labeling which is minus here and plus here. And this is R2. This is R1. This is R2. So if I have a point here, it is getting the label which is half times the first function minus the label by the second function. By the label by the second function, okay, so this one will be minus for both of them. It will be minus. A point here will get a label +½ by the first function, -1 by the second function, so it will be minus. The third function, so it's just a matter of checking. Each time I switch to a new interval, I add a -1 or a +1 for the new interval, so I switch the label. So if the first label was correct, each time I switch to a new interval, I switch the label because I either add +1 or I add -1 alternately. So all I have to make sure is that I have the first label correct. So I guess I'll just leave it to you to check. So the class of T combinations of thresholds gives me all possible partitions of the line into T segments. So this combination is a rich class. Now we can go back to the analysis of the boosting algorithm. Okay, so the analysis of the boosting algorithm will go in 2 steps. And the first step will be analyzing the empirical error. The second step will be analyzing the VC dimension, which will give me a bound on the generalization error. So we'll have 2 steps: the empirical error of boosting, and the second step will be the VC dimension of this class that I'm using in boosting that will give me control over the second term. And for the empirical error, I'll just cite a theorem here that says that if WT, the weak teacher that I'm using as a subroutine, is a gamma weak teacher, a weak learner, for the sample S, meaning for every distribution D over S, there exists a, if I do the weak teacher on this distribution and S, it has arrow at most half minus gamma with respect to ds. So D tells me the weight of every point, S tells me the label of every point. So if the weak teacher can give me error at most half minus gamma for every distribution over the sample, then for every t, for every number of iterations t, I will get that the arrow on the sample, the LS of the end result, sine of sigma WT HT, that the algorithm will give me, is at most, and here we have another is at most e to the minus 2 gamma squared t. So let us just look at this formula, and I think we're running out of time. So what this formula tells me is that if I run for t iterations, my empirical error goes down exponentially fast with t. So the empirical error of this combination zooms down to 0 very fast. The empirical error goes down exponentially fast with t. With every new iteration, it gets smaller and smaller and smaller. However, there is a cost to making many iterations. What will be the cost to making many iterations? What may be the cost of making many iterations? Yes? The VC dimension. Because our true error, so this error goes down to 0 with more and more iterations, very fast. But our true error also depends on the VC dimension of this class. And the VC dimension of this class will grow with the number of iterations. Because as we have more iterations, we get a richer class. So what we will do next time is analyze this VC dimension and get a formula that gives us some trade-off that tells us how many iterations would we like to go for. OK, have a nice weekend.